We already have the data in our calculators, so the box plot is going to be very easy. All we have to do. Why couldn't I cough during the break? I don't understand. So all we have to do is come up with a 5-number summary, right, to create the graph. Now, we're already developing a little bit of proficiency working with the stat plot functionality on the calculator. So let's kind of live in there for a little while, all right? Because we know StatCalc 1, that function that gives you the mean and standard deviation from last class, that function will also give you the median and the quartile values and things like that, which is great. But it's not going to give you the picture. I want the picture. I want the whole shebang. All right? That's the name of the game. If I'm going to use a calculator, if I'm going to make the investment, buy this calculator, I want it to do work for me. All right? I want it to get me the A in this class. I don't want it to just kind of help me along the way. I want it to do the job for me. All right? That you have that mentality with this calculator. Put it to work. Make it earn its keep. All right? So second y equals, all right, stat plot. Enter on the word on. Oh, sorry, plot 1. So same menu as before. All right? Hit the down arrow. We're going to go to the one that looks like a box plot. Okay. Just hit enter. And then go into the type and go to the middle one in the bottom row. It's the one that has the box with the 2 little line segments coming off of it. Okay, that's known as the official name is a box whisker plot. Most people in the world of statistics agree that sounds stupid, so we don't call it that. We all call it just a box plot. Oh, it highlighted the wrong thing. Second one on the bottom. This bad boy right here. I never did that. So if you're on the word on, hit the down arrow, then keep hitting the right arrow until it puts you into the second row. Yeah, it's weird. Yeah, it's so weird. I don't know why it does that. Box plot. Yeah. I was trying to time the blink. All right, I got it. There it is. All right. So then once you do that, same process as the histogram. All right, or at least for a time anyway. You can hit the down arrow, then you got to deal with that alpha lock thing again. But if you don't hit the down arrow, then you can just hit zoom 9. Okay, so zoom stat. If you just build that muscle memory, zoom followed by 9. Immediately after you hit the zoom, hit the number 9, and it'll bring up this graph. And just like that corny joke I was talking about before, we're looking for that print option. We don't have it, so we need to get this graph onto our papers. The good news is it's a lot easier to put this on paper than it is to put a histogram on paper. Different. You got something different than that? Ah. Yeah. Let's take a look. Oh, okay. So you do that. You did this. When you come to this, then you gotta hit enter. Then zoom out. All right, so good looking graph right there. So just copy and paste it onto your test paper and you're good. Now, so trace. Trace is the name of the game. So hit the trace key, and then you can hit the left and right arrows and get all the important values for your data set. Or I'm sorry, for your graph. We already know the important values for the data set. So we want to write these values down somewhere. I'll just put them on in the margin somewhere. The minimum is 0. I don't think you needed a calculator to tell you that, because the minimum is the smallest value in the data set. So, sorry? Right, you got to hit the left arrow. Oh, you got to trace, and then the left arrow. So then hit the right arrow. So we got our minimum value. Hit the right arrow once. We'll get Q1 as soon as my pen works.
So from this right arrow.
From that, you hit the right arrow. Yep. 53 is that number. Hit the right arrow again. You get your median, 77.5. So 77.5. Right arrow again. You get Q3, which is 90.5. And then the final value, which is the maximum, which is 100. And again, some of these values I think we'll call common sense. When we're talking about minimum and maximum, smallest and biggest, you just look at the data set, you know that the smallest number there is 0 and the biggest number is 100. But the other quartile values, that's where you want the calculator to do the work for you. Now, again, for a 20 unit data set, maybe not. Maybe you don't need the calculator too much. But for 30 value data set, 100 value data set, decimal values, yeah, definitely. All right, so now we got to get this on paper, the actual graph. So what we want to do is create a scale that'll get us from the minimum to the maximum in even increments. Now the calculator did that, but we could easily do that too. I want to go from 0 to 100, and I want to go in even increments, convenient increments. So 20s, 25s, 10s, whatever you can think of. All right? Your brain's going to take you in a different direction. I like to kind of go by halves. So what I'll do is I'll plot the minimum, I'll plot the maximum, I'll split it down the middle. That's 50. I'm not worried about the quartile values yet. I'm just coming up with a scale. All right. 25, 75. So if my minimum was 0 and my maximum was 1,000, I would go 0 to 1,000. I put 500 in the middle, then 250 and 750. All right, you do that for anything. All right, break it up by quarters. All right, so scale must underline must, as soon as I spell it correctly, must have even increments. That is not how you spell increments.
And starting numbers.
The spacing.
Spacing.
All right. So, but I've seen it before on tests. Lots and lots of times. You got to be very careful about this. This will cost you points. You don't want to do this. People will just put their 5-number summary as their scale on the bottom and just draw a box above it. And just try to make it kind of look like that and say, I did what he asked. You didn't. You didn't. Okay. It's got to be even increments based off the minimum and the maximum only. And then we plot these values in relation to those numbers. All right. So the 0 and the 100 are going to be very easy. Plot the 0 somewhere. It doesn't matter how far above you go. You could go right on the line if you want. But somewhere in space above the 0 and somewhere in space above the 100. See, in the calculator, they went like 9 units above. There's no rhyme or reason to why they chose that distance. Like, they could have gone 2 units above. It would have been perfectly fine. All right. They just tend to skew towards the high end of the screen. All right. So just somewhere above the line is fine. Just wherever you plot your points, plot them on the same level. All right. 53, you got to eyeball it. All right. I know 53 is closer to 50 than it is 75, so right, yeah. Give or take. 77 and a half, closer to 75 than it is 100. 90.5 is closer to 100 than it is 75, so I'll put it right there. It's really just a neighborhood play. All it is that it's saying, just get that point in the neighborhood of where it ought to be, and you're not going to have a problem, right? Because again, what I said with the histograms, in real life, you're not doing this by hand anyway. You're just demonstrating the skill for me. And then in real life, you're going to Excel, you're going to Google Sheets, you're going to some high-powered industry software that I never heard of. All sorts of possibilities. This part of it is like a constellation. That's the best analogy I can think of. Like 3 dots in the sky. You're like, oh, look, a line. Like, no. Oh, the Big Dipper. No, that's not what it is. It's like somebody along the way said, yeah, let's just put a box around the middle 3. That'll show like most of the data. And then we'll draw a line for like the extreme values. And then where the median is, we should probably identify where that is. So we'll just draw a line there. We should give it a name too. It's got a box and it's got 2 lines that kind of look like blisters. So let's just call it that. And I kind of feel like they had like that California dude kind of thing going on when they were saying it. They're like, yeah, man. I think like there's like 3 dots. I think we could put a box around that, dude. And then like we put a line. Like just 1 line. And then we'll put a horizontal line. Totally lost. You know, so that's where it came from. So if you take the 3 points, put a box around it, draw a line through it, then feather it on out to the extremes, and there you go. That's your box plot. Why do we need to draw the box? I had no idea. The California dudes, they came up with it. All right. You probably just figure out everything you need to know just by plotting the points, but it's not a box plot if you don't put the box in. All right. So that's that. And you're pretty comfortable after you create the graph, even though it's like shoddily drawn. It looks kind of sort of like what the calculator said, so we're feeling pretty good about it. Full credit.
We just say we don't need to write the box.
No, I'm saying conceptually, theoretically, in real life, probably not. But if you're asked to create a box plot on a test, you gotta have a box. Yeah. and hopefully you'll hear my California dude impression going off. So, like, put the box around 3 corners. They're doing a Bill and Ted reboot. Okay, so nobody knows what that means. All right, cool. All right. Bill and Ted's Excellent Adventure and Bill and Ted's Bogus Journey. Keanu Reeves and the other guy. I can never remember his name. Alex Winter. Yes, very good. It's one of those names like I don't remember it, but if you give me the multiple choices, I got it. But yeah, they're rebooting that. Not rebooting it, sequel. They're doing a sequel, and they're doing a sequel on the Matrix trilogy. So they're doing that again. So Keanu Reeves is back and better than ever.
And they just did the John Wick movie, right?
Chapter 3, yeah. Yeah, that was good. I saw that on the airplane. That's some violent stuff. Like, man, they have no problem, showing all the stuff. But it's a good story. So then we have the STEM plot. STEM plot, well, if you're starting to not like this whole calculator business, and maybe starting it's like me just being optimistic about this, like you've not liked it the whole time and you're just like enough with the calculator, then maybe you'll like these because you can't use a calculator for either of these. There's just no functionality on the calculator for it. These are supposed to be quick, easy ways to get a sense of the distribution of the data without having to actually do a full-blown graph. All right, so you just want to get a sense of the data. It's quick and dirty, but it gets the job done. All right, that's what the stem plot and the dot plots are all about. All right, so the stem plot. This one, I think it seems like, all right, now you're just making stuff up. Like it's going to go into that category. And from a teacher standpoint, like if I were teaching all different types of graphs, and then I taught everything that I could teach, and I still had like 20 minutes to go in class, and I was like, all right, I got to teach them something. Let me make up something. Let me see if I could fool them into thinking that this is the graph. That's what this would come off as. All right, this is going to seem like, all right, this now you're just making stuff up. All right, so we're going to write stem here, and we're going to write leaf, or if you want to go plural, you can go plural, leaves. But I just write leaf. All right. Now, the stem plot is also known as a stem and leaf display. But we call it stem plot for the same reason we call a box whisker plot a box plot. Because stem and leaf display sounds stupid, box and whisker plot sounds stupid. So box plot, stem plot sounds more concise, sounds more mathematical. All right. So what are the stems and what are the leaves? What we do is we take any number and we develop a convention by which we partition that number. All right. Partitioning just means splitting. All right. So for example, because I can't zoom in on this anymore for some reason, you just gotta, I guess, squint if you can't see. But I'm going to draw a line right down the middle of the 8. So I'm going to split it between the 8 and the 0. It's a 2-digit number. If I'm going to split a 2-digit number into separate digits, there's a natural way to do it. Okay, right down the middle. If you get into 3 digits, 4 digits, 10 digits, it's a different story. You kind of pick and choose where you put the line. There's no wrong answer. You can put it anywhere you want, as long as you do it the same way for every number. So, for the 91, I would put my line between the 9 and the 1. For the 90, between the 9 and the 0, and so on. All right. You don't have to actually draw the lines down the middle, as long as you know what the idea is. And so, the way to handle that for the reader of your graph is just off on the side somewhere, you make a little key. telling the reader of the graph, because if you publish an article and put a graph in that article, you don't then include the entire raw set of data, because it would be like, here's my one-page article, and here is a 30-page data set to go along with it. That doesn't work. So you give the graph, and you give a way of interpreting the graph. So what I do is I choose an example from the data set, like 9/0 means 90. And that's because, depending on the nature of the stem plot, 9/0 could be 9.0, or it could be 9 to the 0th power. You know, people can go in a lot of different directions with these stem plots. All right. Then the big question becomes, all right, well, we got to figure it out for the 2-digit numbers. How do I handle it for a 3-digit number? Well, just do it the same way. We have the ones place. And we have the tens place. When we split it down the middle, that's what we ended up with. When you split a 2-digit number down the middle, you have the tens place on the left, you have the ones place on the right. So when we get to the 100, we'll draw the line between the ones place and the tens place. Incorrect. There we go. All right, so we got that. You can do that for any 3-digit number now. You're just following the same rule that you established for the 2-digit number. So then the natural follow-up question is, all right, we got the 3-digit numbers. How do I handle a 1-digit number? Well, a 1-digit number can be transformed very easily into a 2-digit number. Any 1-digit number can be 2 digits if you put a 0 in front of it. So now it's 2 digits. Put the line right down the middle. All right. You can't put the 0 behind it, because if I take like the number 1, if I put a 0 in front of it, it's still equal to 1. But if I take the 1 and put a 0 behind it, it's not equal to 1 anymore. All right. So it does matter where you put the extra 0, but you can take a single-digit number and make it into a 2-digit number. So the stems are they're going to be the list of stem values, left sides, going from the smallest stem to the largest stem. All right. So what we have here, that's my smallest stem. And right here, I have my largest stem. I'm going to make a raw list going from my smallest to the largest. So 0 through 10, I'm not going to skip any along the way. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You got to extend the line, extend the line. But I'm willing to bet that I'm the only person that can't seem to get the spacing down on this. All right, so we have our stems. Honestly, when people lose credit on a question like this on the test, they only lose credit because they forget to put the key in. So you're going to get this right. You just have to remind yourself to give that example, telling the reader how to interpret the graph. Right? That's the one thing you're going to have to worry about from a student standpoint. Okay. So the leaves. What I'm going to do is I'm going to work my way through the data set. For each stem value, there's a row, a blank row. I'm going to include the corresponding leaf value. All right? Doesn't have to be in any particular order. All right? So I have an 8 with a stem of 8, a leaf of 0. So in the row for 8, I'm going to put a leaf of 0. Yeah, we're going to go right down the line. So the 9 has a 1, 91, 91, 90, 90, 51, row 5, put a 1 in there. Keep the spacing consistent. You don't need commas or anything like that. And in fact, commas are not incorrect, but they are unsightly. Right? We're trying to make a graphical display. We want it to look reasonably nice. I mean, as nice as you're capable of doing it. Like, you don't want to go out of your way to make it ugly. Like, if you got a shaky hand like me, then it's going to look ugly no matter what. You don't have to make it more ugly on purpose. All right? So, nice even increments. So keep the spacing between numbers consistent, because this is, after all is said and done, a graph. All right? It's supposed to give us the shape of the distribution. So we have the 51. So 75. So in row 7, the number 5. 83. So in row 8, the number 3. There's 283, so I need that again. In row 8, we have the number 0 for the 80. I have 2 95s, so in row 9, I'm going to put 2 5s. I have a 100, so in row 10, a 0. I have the double 0, so in row 0, I'm going to put a 0. I have another 100, so in row 10, I'm going to put a 0. I have 2 75s, so in row 7, I'm going to put 2 more 5s. Again, no particular order in the leaf column. The stems have to be in increasing order, but the leaves can be in any order. All right. 56, row 5, include a 6. 42, row 4, the number 2. 25, row 2, the number 5.
55.
Say it again.
55, you put 1, a 6. I have 51? Oh, yes, sorry.
Oh, there. Okay. I thought I screwed up too. So we have an 11, and then we have a 55 to finish it off. All right. So, again, I prefaced all this by saying, yeah, this is going to look like, now you're just making stuff up. Here's a graph. What does this graph tell us? It's actually kind of weird, but this graph tells us a great deal. This is a sideways histogram. It doesn't have the bars. All right, if you look at it sideways, you would have, if you were to create bars, you would have a bar with a height of 1, 1, 1, 0, 1, 3. There's 3 numbers here. 0, 3, 4, 4, 2. All right? The only question would be, well, what histogram does that correspond to? Because that doesn't look like the histogram we created on the previous page. Well, that histogram went by 20s. This histogram is going by 10s. All right? A stem plot, if you're dealing with ordinary integer values, it's going to go by 10s because each tens place is an interval of 10 values, naturally. All right? So the number 1 is going to cover everything going from 10 to 19. All right? The number 2 is going to cover everything going from 20 to 29 and change. All right? So you're automatically getting a histogram, a sideways histogram, that is broken up in intervals of size 10. All right? It's quicker than a histogram, but only for small data sets. All right? And the reality is, nothing's quicker than technology. So the fact of the matter is we had to write down all of these numbers. All right? Just physically, the act of writing all the numbers down is equivalent to typing all the numbers in our calculator. So just by writing this down, it took more time than creating a graph on a calculator. All right? So if you don't need to produce a graph on paper, even if it's a small data set, do it on the calculator, because if all you need to do is just get a sense of the nature of the distribution, and you just want to look at it for your own purposes, take a look at the picture. You don't want to waste your time doing this. But if you need to get a graph down to satisfy a question says create a graph. I need to do one quickly. This might be the way to go. Just don't forget the key. All right? Because if you don't have the key, the graph, I don't want to go too extreme and say the graph is meaningless, because that's not fair. There is meaning to it. You still have shape and center and all that stuff, but I don't know what the numbers mean, right? Because I'm looking at this, I see a 4 and a 2. 4.2 miles, 4 feet 2 inches, 4 hours 4 hours and 2 minutes. Like I don't know. Like what are the units of measure here? All right. So the key is very, very important. And in fact, like it's necessary.
You want us to restart this class behind and zero. Is it you give us the point at us, so we have to separate the numbers by the.
Right. You're telling me that this is how you separated the numbers. Because and for 2-digit numbers, it's pretty obvious. So it's almost borderline like unnecessary, but when you're dealing with 3-digit numbers, like if I gave you a table of data that had all 3-digit numbers, you might put the line after the first digit or after the second digit. I don't know. So the key is you telling me I chose to put my line after the first digit, for example. So 80 has a stem of 8 and a leaf of 0. So I went to the row that says 8 and I put the number 0.
Because the leaf is 0.
Correct.
How did you get the 3?
When I was going through the data, eventually I got to the number 83, which has a stem of 8 and a leaf of 3. Now the dot plot is a little bit of a different story. It's the easiest one to create, but sometimes it's kind of a pain because the scale needs to account for all the values on the interval. All right. So in essence, whatever scale you're using for the box plot is what you're going to generally use for the dot plot. The problem is there's a lot more estimation involved, and that can be. I'll just go with annoying. I'll settle on that word. All right, so here is 0, here is 100. And your scale, again, this is how I like to make my scales. Your scale can be by 10s, it could be by 5s. I mean, if it's a small enough range, like if it's only going from 0 to 20, maybe you go by 1s. All right? I only went by 25, so it's going out to 100. I don't want to go by 1s to 100. All right? So, this is the part that it's going to, it's really going to make or break whether or not you're even going to look at this as a graph that you'd like to use if you had a choice. All right? You're going to plot a dot over each number on the scale corresponding with the value of the data set. And if there's more than one at a particular location, you'll plot a dot above that value. So if I have 10 80s, I'm going to have 10 dots right above 8. But the thing is, I have a scale going by 25, so I have to estimate where 80 is. So I can't lose track. So if I have 80 and 83, I can't lose track of what's what, 80, 83, 85. I might accidentally plot points at the wrong place. So the way I handle it, it makes it look a little sloppy, but it's a sacrifice that I'm willing to make. I plot a point right above where I think 80 is, and then right in small digits below on the scale, I'll just chuck a little 80 in there. Even if it doesn't look scale-wise where 80 would supposedly be, I'm going to put it there anyway. All right. The next one is 91. So I'm going to ballpark the 91. Now, I don't know where 90 is, but I know it's not where 91 is. It's got to be a little bit to the left of that. So I'm going to put that just a smidge to the left. A little bit above it, yeah. then 51. Now, you'll notice that I didn't write 90 on the scale below because it's going to make it too messy. I'm just putting it there because I figure, well, it's right next to the 91. So when I go back and look at it, I'm gonna reason out, all right, that's got to be the 90. All right. The next one is the 51. So I'm gonna ballpark it, indicate that that's my 51. So if I had to plot 52, I'd just go right next to it. 75, that's easy, that's already there. 83. Now, I'm going to look at my data set in its entirety and just make sure that there isn't a bunch of other 80s that I have to plot in there. It looks like there's only one other value, unique value in the 80s. So I could just plot this here and know that that's my 83. But if you're really uncomfortable with that, squeeze it in there and just write 83. All right, and there's two of them, so I get another dot. Then I go up, I got another 80, so a dot, another dot for the 80. Let me get rid of the stray marks so you don't think there's even more dots. Then a 95, all right? So just got to be careful not to paint yourself into a corner here. I got to get a 95 in there. I'm going to just pop it right here. I'm not going to label it because I don't have the room, but I do have two 95s. So I'll put the second dot above that. 100, 0, another 100, two more 75s. And what's happening is the distribution is taking shape, but it's an ugly graph. But we'll take ugly. Ugly's okay. Because you just need a quick and dirty way of getting a sense of the nature of the distribution. All right, plotting 56 now. Just estimating where I think it is. 42, same deal. Right about there, I guess. 25, that's one of my benchmarks, so that's fine. 11, there's nothing in the neighborhood of 11, so I could just plot that. I don't even have to label it. And then there's a 55, which I know is just going to be a little bit west of the 56. All right. So in terms of mathematical rigor, you look at this and say, oh, that's not even remotely as technical as something like the box plot. But if you look at it, it tells you a lot of information. Now, I promised you earlier that the graphs would tell you everything you needed to know about the data set once I gave you a little bit of context. All right? And that context is that this is a class set of test scores. All right? No surprise. Okay? Because I'm a teacher, you know, like, what do I default to? Class set of test scores, of course. All right? And you look at the numbers, the lowest is a 0, the high is 100. If you had to take a guess, that would probably be in your top 5. All right? So this is a class set of test scores. You can look at every one of these data sets in the form of the graph and now have a good sense of what happened in this class. All right?
Professor, the dot between 0 and 25 is my 11, right?
That's the 11, yep. You have a very good sense of what happened in this class without me getting into things like mean, standard deviation. I didn't talk about any of those words. I used the term standard deviation once, like 2 hours ago. And we talked about it a great deal last class. All right? But now it's like, wait, we're looking at this, but the concept of standard deviation is buried in there. How is the data spread out? All right? So the data is spread out, we know that, but how is it spread out? All right? So regardless of which graph you're looking at, I mean, you can look at the histogram, you'll get the same idea. But if you just want to look at this page, you have the box plot. You see that tail pushing off to the left-hand side. You look at the stem and leaf display, sideways. That tail off to the left-hand side. You look at the dot plot, tail off to the left-hand side. What you're looking at is a graph that is skewed, all of the graphs, all graphs are skewed left. All right, so the tail is to the left. All right, the tail is to the left. All right, so in a standalone instance, not the end of the world. You don't want to be giving away a quarter of the credit on every question. So, you miss a small detail every once in a while, it's not going to kill you. But if you're consistently missing small details, that's, like, I understood all the material, but I still got a 70 on the test. What the hell happened? It's because you're missing the small details.
Do you label anything on the book?
No, that's the entirety of the labeling. So that's the good thing about the dot plot. You get away with a lot of stuff because all you're doing is just dotting it up, and that's the end of it. Right. So the tail tells us where the data is feathering out. So you have a ton of data on the right-hand side, and then a couple of stragglers over on the left. All right, that's what skewed left means. Now, if it were the other way, you'd have a bulk of the data on the right, and the tail would be off on the. Bulk of the data on the left, and the tail would be off on the right. That would be skewed right. All right. The normal distribution, where it's at that nice bell-shaped curve, that doesn't tail in either direction, right? Just because it has just what seems to be a tail doesn't mean that it's skewed in any particular direction. Bulk is in the middle.
On the test, you want us to write the numbers so you both could write 80, 90, and all that stuff.
I don't. All the numbers I wrote in red were just for me to keep things straight. I don't need to see that. If it helps you, then definitely include it. I encourage you to do it, but it's not a requirement. All right. But the nature of the distribution, the nature of the spread, tells us that this class generally performed well on the test. Right? I don't even have to look at averages. I mean, you can look at the median if you want. That's fine. It's there. But we could see that the bulk of the data is in the passing range, high passing range, 80s and 90s, 100s, things like that. And then we had a few that were in the bottom. All right, we got a 0. What could be a cause of 0? Well, it depends on the class, but generally, it's my thinking that you either cheated or you cut class. Like that's generally how you got a 0. Like most people don't show up, sit down, take a test after having studied, work through the whole test, and then earn a 0. It generally doesn't happen that way. I suppose the one instance, the exception to that would be you just took a multiple choice test and it was the hardest test in the world, and somehow you got every single question wrong, right? And there was no curve. And actually, even if there was a curve, zero still curves to a 0. So that's that. So there's that. The person who got an 11, what's going on there? The 25, the 42, the 56. Okay, we got a couple of people who flunked the test. What's going on? What were the causes of those failures? All right. Just by looking at the distribution of data, and oftentimes you can just pull it out from the numbers themselves. You don't actually have to create the graph. Like I would like to think that as I'm grading papers, I don't have to be like, all right, I'm grading all these papers. Can't wait to see what the graph says about this because I really have no idea how my students did. Like I just graded a paper and the student earned an 11. I need to talk to that person. I know what happened. All right. I just graded 13 papers and they were all 10 out of 100. Okay, I did something wrong. That's a different story. But if I have, let's say I'm an administrator, and I have Regents exam scores, or AP exam scores, or master's theses, all these grades, and I'm trying to analyze them. They're not in context. They're just numbers, thousands of numbers. A graph is going to help me, right? It's going to, I don't have to worry about these people. I got to worry about these people. Now, I'll take that data, put it in a separate distribution, and try to flesh out even more what's going on. All right? So you get everything you need just by looking at the display, as long as you know how to read it. All right? So we look for 4 things when we create a graph. All right? 4 really important things. And you're not going to like this, but it's life. There's lots of things you're not going to like. Center, shape, spread, and outliers. All right, these are the 4 things that you need to address anytime you create a graph. Must be addressed. I'm going to change any to every time. You create a graph. All right, so that's the part you're not going to like. Good news, bad news. There's always good news, bad news, right? Which one do you want first? The bad news. Everybody wants the bad news first. I gave you the bad news. Now here's the good news. You've already addressed it. You just didn't necessarily realize you were doing it at the time. We just created, 5 graphs? Somewhere in the creation of these 5 graphs, we answered all of these questions. All right? So, it's just a question of, in what way? Or at least, let me rephrase it. I don't want to make it too sunshine and rainbows. We have taken steps or gotten all the information necessary to answer all these questions. All right, that's a little bit better. Center, it's there. I'll show you. Let me just make sure it's on pointer, not pen. Oh, come on. How is that a useful feature? Get out of here. There's our center, right? Addressed. There's 3 measures of central tendency that we use, mean, median, and mode. I didn't say which one you had to use, right? The median has been accounted for. Shape. Center means mean, median, or mode. The fact that a box plot requires you to come up with the median anyway means that you already have that. All right? Spread. So we have center, we have shape. When we talk about skewness, we address shape. If you say that there's no skew, you're addressing shape. All right? So you got that covered too. The spread part. All right? We could go back to the box plot. If you haven't gotten the idea that I'm really pushing hard towards this box plot idea, as a box plot being the best kind of graph, spoiler, box plot is the best type of graph. Use that one anytime you have a choice in the matter. There are some exceptions to that, which we'll talk about next class, but generally as a rule of thumb, that's where you want to go. Spread. There are a variety of different types of spread. We learned about one really important one last class, the standard deviation. Right? You can compute that if you want. And we also learned about another type of spread, the interquartile range, which is just simply the 3rd quartile minus the 1st quartile. So you're getting the spread from your 5-number summary. So we just need to take 90.5 and subtract from it 53. Is that 37 and a half? Ish. All right. Again, measures of spread are comparative, so it's just a number at this point. It's not an overly meaningful number until I give you another set of 20 test scores from another class, and then ask you which classes perform better on the test. That's when that number is going to really have more meaning. All right. Then the last thing is outliers. You remember right back to page 2 in the package. There's a big juicy formula for outliers. We worked through it. It sucked. No, it wasn't that bad. It was fine. It's just a formula. You plug numbers in and everything's good. However, there's a much simpler way to do it. Except I couldn't teach it at that point because I hadn't taught you about stack graphs. So this is the very last thing we're going to do today, and it's the grand finale. I think you're going to like it. I hope you're going to like it. It's called a modified box plot. Ooh. Chinese fireball. Ooh. So second y equals, spoiler, it will tell you the outliers of a data set. All right? It's not going to just give you a formula, give you a recipe, give you a way to figure it out. It's going to say, this is the outlier. Write this number down. What more can you ask for? Especially if you remember that formula on page 2. All right? And if not, at some point, take a look at page 2 of your packet, or page 3. All right? So it's in the stat plot. So second y equals, just like before. Hit enter on plot 1. It's still on from before, so we're good there. If not, you turn it on. Hit the down arrow to get into plot types. All right, we learned how to plot a regular box plot. So we know that that's that middle one in the bottom row. Which one do you think is the modified box plot?
The one to the left.
The one to the left, the one right next to it. What do you think those 2 little dots symbolize? Outliers. All right. So we're going to create this graph, and if 2 little dots show up in the graph, we have outliers. If 2 little dots, well, actually, maybe not even 2 little dots, 1 little dot, whatever. Any dots show up in the graph, you have outliers. No dots, no outliers. So I'm going to hit enter on that plot. So it's on. And I'll just chuck it down here so we have it. I hit the wrong thing. Sucks the life out of me every time that happens. All right, so modify. All right, so once you select this one, box plot, modified. The one we're working with now is the modified box plot. So once you select that option, hit enter on it, and then just a quick zoom 9. Looks exactly the same. What did we do wrong? Nothing. Absolutely nothing. All right. So I'll explain. With a giant graph. Graph looks the same. Modified box plot looks the same as an ordinary box plot. That's what we write. Modified box plot looks the same as, you could say regular box plot. You can just say box plot. If you don't have modified in front of it, it's okay. I'll say ordinary. I like that word. Therefore, 3 dots in the form of a triangle means therefore no outliers. If you had a loose dot show up, that would have represented an outlier. All right, so you would have seen a stray dot or two on the high side or the low side. To figure out the value of the outliers, well, it's pretty easy. You can just look at your data set. If there's 2 loose values on the high side, they're the 2 biggest values in your data set. But if you want a more technical way, just hit trace and scroll just like you would if you wanted to find the 5-number summary. All right, just scroll right onto the dots, right, and that's it. So, waste of time to teach you about the outlier formula? I don't think so, because you learn what an outlier is, how to compute it, what its meaning is, and all that stuff. But now we can get it. We can get it quickly. And we can interpret. We can get into the interpretation part of statistics quicker without getting bogged down by the calculation. All right, that's my philosophy with stats. Other teachers don't believe the same thing. And in fact, funny story, student went to the tutorial center, was getting help with statistics, and a teacher, I don't even know who it is, it's not somebody I know, was commenting on pacing. They were like, oh, you're only on this topic? Well, my class is on this topic. And the student told me that after the fact, and I got a little heated about it, but I've been telling my students ever since that if anybody tells you when you go to the tutorial center to get help or help from another teacher, if they say, oh, you're only on this topic on this date, I've been teaching this for 20 years. I got it down. Your response? My teacher said you would say this. The answer he told me to say, these are not my words, he said to say, Professor Can actually cares that his students understand the material. Okay? So, as I flip the table over, yes, absolutely. So that is the reality of it. I structured the course so that you get the meaningful aspects of statistics, don't get bogged down in the calculation, and you can directly apply it in real life immediately. You don't have to wait 3 courses down the road before you can start using this stuff. That's how important I find this material to be.